Last class we looked at the different kinds of cascode current mirrors. We looked at, right, and we looked at how to bias them. We looked at how to bias them. We looked at the normal cascode. We looked at the high swing cascode. Okay. So what we'll do is we'll continue today. We'll continue on that. Maybe I'll give you a couple of more ways to bias that the gate of the upper of the cascode device, and then we'll look at bipolar transistors and bipolar current mirrors today. I assume so. We'll go through it very fast because you've already covered bipolars in the last semester, right? In the last course, towards the end. So you should also already know the basics. Either way, for this course, bipolars, you'll have to know bipolars, but they won't be, what I would say is majority of the modern analog ICs use CMOS, MOSFET based circuits. So you'll have to know those very well, and bipolar also you'll have to know, but it's also easy to pick up, because the bipolar device is quite similar to the CMOS device, except for some extra things you have to remember. Okay? Right, so this is the high swing cascode. We're trying to figure out ways to bias, it's not VB cubed, it's VB3. Okay, so we're trying to find out ways to generate VB3. Okay, so last time we found out that, so you want to have as much swing as possible, so you want to set this VDS. This VDS is already at VGS minus VT at VDSat. You want to set this also to VDSat. This thing has VT plus VDSat, so you need to have VT plus 2 VDSat here. Right? So one way we looked at was to generate using a MOSFET which is 1/4, which has a 1/4 W over L compared to the other devices. But there is one fundamental problem you have to keep in mind. M3 and M0 have experienced the body effect, the backgate effect. So their VTs are actually higher than those of M1 and M2. Okay. Whereas if you look at the VT of M5, which you used to bias, that is it's also lower than the cascode devices. So you might have to design this voltage with some margin in mind. Okay, so in other words, you'll have to find out what the extra body effect is and design accordingly. Okay, so you need to make sure, because if you just design it exactly equal to VT of this plus 2 VDSat, the actual VDS for the lower transistor M2 will be lower. Okay, because the VTs are different. This is one way. Another way is to do this. Call this I naught. Oops. Okay, so now in this way of biasing, what you're going to do is you're going to make sure the W over L of M7, sorry, you have a question? You're going to make sure W over L of M7 is going to be very, very large. Okay, if you do that, VGS7 will become almost equal to VT7, right? So you're biasing it in almost in subthreshold, close to, you know, the moderate or weak inversion region. Okay. So then what is VB3? VB3 is VGS5 plus VGS6 minus VT7. Okay. Approximately it is VT plus 2 VT sat. If you assume so, now M6 and M7 experience the body effect, so their VTs will approximately cancel, and you'll just get VT5 plus VT sat plus another VT sat from this. Okay, but again you have to remember that M7 experiences a larger body effect compared to M6. Okay, so again there will be some error compared to what you want. Okay, in all these cases the way of biasing is only approximate. You will always have to leave a little bit of margin. Okay, so maybe a few tens of millivolts. Yes. You want me to explain the, do you remember what the body effect is? What is the body effect? And the source? No. There will be a threshold voltage change. Remember that the threshold voltage will increase if your body is, so the body of all these NMOSs in the normal process is connected to ground. Okay. The source on the other hand can be ground or higher. If it is higher, then what will happen is the VT of this device will increase. We did this on the first class. Okay. One of the consequences of body effect is the fact that you have the backgate transconductance. Okay, that's actually a second order consequence effect. Right? So the fundamental effect is the increase in VT of any device which doesn't have its body connected to its source. Okay? So now when that happens, you remember that gamma times root of 2 phi f plus VSB minus root of 2 phi f. Remember that? That's the amount by which the threshold voltage increases. Okay? Okay, so now you understand how what happens. So now the main reason why you need to have some margin in all of these designs is because this device has its body connected to ground, which is its source, whereas the other devices have the body connected to ground but the source is higher than ground. So their VTs will be higher. Okay? You can look at figures 5.14, 5.15 for a couple of other ways of biasing it, and the associated text, of course, in the Razavi textbook. Okay, so there are obviously, lots of ways. There are ways to bias the VB3 using a source follower, for example, and a couple of diodes. So you can look at some of these things. Similarly, have you heard of this book, Gray and Meyer? Gray, Hurst, Lewis, and Meyer. Okay, so that is also, if you plan to remain in analog IC design, that's actually a fairly important book. It is a very informative book, but I would say, in my opinion, it is you probably need to be a little bit of at a little bit of an advanced level to understand. Even though it explains all the basics very well, you have to probably to appreciate the quality of the book. You might have to be at a slightly higher level. At this point in time, now that you have undergone a course, you should be able to refer to this book. Okay, it's an excellent book. And of course, Gray and Meyer are some of the pioneers of analog IC design. Okay, in the 60s and 70s. They are two professors at Berkeley. Okay. The name of the book is actually Analog Integrated Circuit Design. The first few editions were Gray and Meyer. Now it's Gray, Hurst, Lewis, and Meyer. Okay. So we'll quickly move on to bipolar devices. I think, so what will happen is maybe, I suspect that today's class might end a little bit early, I'm not sure. But anyway, that's good because the lecture is starting at 9 o'clock. Okay. But we'll quickly review, bipolar devices. So how much of bipolars have you covered in the previous course? Have you covered the basic device level operation? You have. Some of you have not, or all of you have. You understand the device operation of the bipolar very well. Okay. So, and you understand the behavior of the currents and voltages. Okay, I'm not getting a lot of feedback, so you have to, unless you tell me one way or the other, I'll just assume you know and move on. Okay, so that's what I was planning to do anyway, so that's good. Okay, so because we won't have time to go through the details again, so we'll just go through probably just in today's class. Today will probably be the first and last time we'll cover the basics of bipolars. Okay, very quickly. So this is an NPN. Okay. So you have the base. So for an NPN, the normal convention is to assume that the base current goes into the base, the collector current flows into the collector, the emitter current flows out of it. However, there are other terminologies you have to realize. For example, the Gray and Meyer book I was talking about, they use a slightly different convention. Just the direction and the signs matter. Okay, just remember that. For the PNP, the directions are slightly different. The emitter current is nothing but the sum of the base and collector currents with the directions we have assumed. Okay? Let me. This is called the forward active region. Okay. And this is the collector current as a function of collector emitter voltage for increasing base emitter voltage. I'm sure you all remember this. This is kind of the fundamental of the device operation, right? Okay. I should have been. I should have drawn these better. Okay. What is this? The early voltage, VA. Okay, so if you extrapolate all the, so the collector current in the forward active region, okay, first of all, I've actually drawn it to the large slope, you have to, but this is the region, to the right of VC sat is where you actually want to use the transistor. Okay. And in the analog region, the collector current is a weak function of your collector emitter voltage. Okay. And if you extrapolate all the curves, they all meet at one single point, which is VA or the early voltage. So there is something called the early effect. So just like we talked about in the MOSFET, we had channel length modulation. So your drain current was a function of VDS, right? Similarly, in the bipolar transistor, you have something called base width modulation. Okay, the width of the base is a function of your VCE. Okay, because of that, your collector current changes. So this is also quite often represented by your output impedance of the transistor. Okay. Is that clear? So what is the IC as a function of VBE and VC? Some saturation current IS, VT, okay, into 1 plus VA, okay. Where VT of course is KT over Q, right? So now what is RO? You can show that RO is nothing but IC over VA, approximately. Thank you. It was a bad mistake. Okay, yeah. I was thinking of GO. Okay. Yeah, it's VA over IC. Okay. Another thing to remember, unlike your MOSFET, in the case of the MOSFET, your output impedance was a function of the length of the transistor, for example. There were parameters you could change to affect the output impedance. Okay. In the case of the bipolar transistor, the only thing you can do is change IC. VA is actually a function of the process. It's a process parameter. It's not a design parameter. Okay, it's fixed. Okay, it's a fixed process parameter. What is the GM? You can show that it's IC over VT. Okay. Have you studied a parameter called beta F? You studied a parameter called beta, but did you ever call it beta F? Okay. So this is called the forward beta. The idea is it's a large signal quantity, so it's a DC quantity. So it's nothing but the collector current over the base current. Okay. And it turns out, well, of course it's a function of IC. Turns out it's a function of current density. Okay. Do you know what it, if I plot beta F as a function of IC, do you know what it will look like? Will it be constant? Okay, so it turns out it will look something like this. Okay. So there will be a certain bias current, a certain collector current at which beta will be very large. Okay. But the important thing to know is that it is a function of the collector current. Okay. The other thing to remember is that if I decide to change temperature, beta also changes. And it so happens that for the bipolar device, the beta actually increases as a function of temperature. Okay. So this will be 10 microamps and so on. Okay. So now, from this beta f, remember beta f is a large signal parameter. And you would also studied that the small signal beta is actually different from the large signal beta. I'm sure you have studied that, right? Okay. It's also quite common to assume for calculating the operating point, it's quite common to assume that beta f is large enough to be, you can assume it to be infinite, make your calculations to calculate the operating point. Okay, that's very common. Okay, what is delta IB? Right? Delta IB is nothing but d by dic of IC over beta f times delta IC. Correct? So now you can define something called beta naught, or sometimes it's just called beta, which is delta IC over delta IB. At the Q point. At the quiescent point. Okay. So you can define beta naught is d by dac of IC over beta f, the whole inverse at the quiescent point. So in other words, in general, beta naught is not the same as beta f. Okay, even though both of them may be 100 or 150 or something, they are not equal in general. They'll be equal if beta f is constant as a function of IC. Okay. Okay. Now, what is the input resistance? Let's call it R pi. Nothing but 1 over dou IB over dou VBE at the quiescent point. You can show that this is nothing but beta naught over GM. Okay. Do you know all of this? All of you must have studied this, right, in the previous course. So this is the small signal model of the bipolar. Okay, and it's the low frequency model. I think you've already studied the high frequency model with C pi with the capacitances. I found that you've already studied that. Okay, so we probably won't go into that right now. Okay, so next step is we'll study some of the bipolar current mirrors. Okay, and I noticed that you've already studied, in some of them, the very basic simple current mirror. We'll go through it quickly anyways, okay, to find out the differences with the MOSFET case. Okay, this is a simple bipolar current mirror. Okay, what is I out? Nothing but IC2. Okay, so now IC1 is actually, let's write the equation slightly differently. So first of all, we know VB1 is the same as VB2. Okay, that we know. Correct? So we'll write the bipolar equation slightly differently in terms of the logarithmic equation. So it's VT ln IC1 by IS. So the ratio of the two currents, of the two collector currents, is nothing but the ratio of the two saturation currents, right? What is the saturation current a function of? It's a function of the emitter base junction area. Okay, it's also a function of other device parameters, but your primary design parameter is going to be the area. Okay, so if you want a multiplication of 2, you'll use a larger area. Okay, or maybe 2 devices. Okay, now for simplicity's sake, let's just start off by assuming that these two transistors are identical, because we want to find out what happens if the two are identical. What is the current ratio? Okay, so the two collector currents are equal and equal to the output current. If you write KCL at the collector of the first transistor of Q1, right? So the collector current is nothing but IN minus IN is nothing but IC collector current plus the sum of the two base currents, right? And you know the relation between the base currents and the collector currents. And in this case, the two collector currents are equal and also equal to the output current. So it's just I out times 1 plus 2 over beta F. Okay. And now this gives you the gain error of a simple current mirror due to finite beta F. Okay. Now it may seem that beta F is, a couple of hundred and it's not a problem, but this is actually a function of the number of mirror legs you have. If you have more number of mirror legs, you'll have more number of transistors for which you'll have to supply supply the base current. So this, 2 over beta F will become 3 over beta F if you have one extra leg. For n general legs, you'll have n plus 1 over beta F, right? Okay. Now if the two things aren't identical, okay, now then what you'll have to do is, you know that the ratio of the two collector currents is nothing but the ratio of the two saturation currents. So you can get the overall mirror ratio, overall output current as a function of the input current and the ratio of the saturation currents. Okay. You can go through the same process. You can show that. Okay. For a simple current mirror, which is not identical. Okay. You can show that the output, this is the relation between output and input currents. Okay. So this is the error due to finite beta f. So next we'll consider the error due to output impedance, because that is if you compare a bipolar current mirror and a MOS current mirror, this is one primary difference. MOSFET doesn't require any gate current, right? Whereas the bipolar does. So there is fundamentally, even if the two voltages are equal, there is a fundamental mismatch in the bipolar. Okay. But now if the two voltages are different, as with the MOSFET, due to the output impedance, you'll get an error. Okay. Okay. And now the two early voltages could also be slightly different. Okay. Or we'll just assume it to be the same. Okay. So we'll just assume that it's the same. You can again go through the math and you can show that you'll have the same term. But you'll have an extra term, which is the old expression times 1 plus VCE2 minus VCE1 over VA. Okay. Obviously, if the two VCs are equal, then you just go back to the old expression. Suppose I plot I out versus V out. Okay. It will have some dependence, and you'll find that you actually have DC balance only at one point. Okay, this is the diode point, which is okay. So now you can, next we'll find out what the error expression looks like. You can calculate it out, okay? I don't want to go through all of that, but I'll give you the expression. This is of course the error expression, but if you simplify it further, you can show that it's nothing but, actually you'll get two terms. This is the first term, yes. Okay. Let us say beta f is infinite. Okay. Then you don't have this term at all. Ideally, you expect only I out equals IS2 over IS1 times I in. Okay. However, I out is going to be different. Even at infinite beta f, I out is going to be a function of V out. Thanks to that second expression. What is V out? V out is nothing but VCE2, right? Okay. The two currents will become equal only at the diode operating point, which is VBE1 equals VCE1. Correct? So when VCE2 equals VCE1, which is also equal to VBE1, that is the only time when the I out will be equal to the value which you want. Okay? At all other points, in reality you want the two currents to be identical, but they'll never be identical. There's only one point where they will be identical. Okay? Is that clear? Well, DC balance, the two DCs are equal. That's why it's balanced. Okay. Okay. So this is the error term in the current. Why do you have this negative sign here? Okay. So what if beta f is large? No, that is okay. But what is the significance of the beta term in the error? Does this minus sign have any significance for the error? Sorry. So ideally you want your current to be IS2 by IS1 times IN, right? What is the current mirror doing? You have an input current, you want to completely mirror that to the output, right? If you don't completely mirror it, there is going to be an error. And this is that error. So ideally this is that point, but suppose your operating point is here. This will be the error. If your operating point is here, this will be the error. Okay? What is the significance of this minus sign? It's actually fairly straightforward. Since you have, right, if you have beta f, if you have finite beta f, the current is always going to be lesser than the ideal value you want. Correct? So therefore you have a negative sign. The error is negative. However, if you look at this term, it depends on delta VCE. Okay? If VC2 is larger than VC1, then this error term is actually going to be positive. Whereas if it is less, it's going to be negative. That you can clearly see from the previous graph. Right? What is V out min? Minimum V out? This is just the VC sat of Q2. This is typically 0.2 volts, somewhere around 0.2 volts. Okay? What is Rn? The input resistance of the input impedance of the current mirror. Sorry. Okay, you can show that the input impedance, it's just a diode connected transistor. approximately 1 over GM. What is R out? Just R naught, R naught 2. Okay? Okay. Now it turns out you can do a little bit better. You've also studied this, the beta helper. Okay, this is called a beta helper because you don't want the error term due to the base currents. Okay, because of that you add the source pole over here and you can show that the overall error, overall current error goes as the inverse of the product of the two betas. Okay. So in other words, the bias current for Q3 is nothing but IB1 plus IB2. What is the base current drawn by that? That over beta F3. Okay. So in other words, the error in this reduces further. Okay. Now one thing you have to remember. Remember this curve we drew? So it turns out beta F is actually a function of current. Okay. If your collector currents I in, I out, they are all of the order of, let's say, 1 milliamp. Beta F is 100. The base currents are going to be of the order of 10 microamps. If you go to 10 microamps, the beta is actually much smaller than what you would expect. Okay. So you have to be very careful. Beta F3 will not be equal to beta F1 and 2. Okay. It will probably be much smaller. So to help with that, people sometimes add a bias current I1. Okay. So you set the bias of Q3 such that beta F is larger. Okay. Then you can show that the error term is proportional to 1 over beta F squared. Now again, if you draw the I out versus V out characteristic, the balance point will be different now, because the balance point is when the two collector emitter VCEs are equal, right? In this case, this thing is actually VB1 plus VB3. Okay. So the balance point is different from the previous case. Okay. So now we added the beta helper with the current source. We know how to make a good current mirror. Okay. Next thing is, can you do better? So it turns out if you add degeneration resistors, okay, for the bipolars, you can show two things. R1 and R2, as before, as with the MOSFET, they help to increase the output impedance of the current source. which is good. Okay, definitely you're always looking to make it closer to an ideal current source. But you can also show R1 and R2 actually improve the matching between the two currents. So in this case, as before, if you calculate the error term, okay, it turns out the error term is actually an inverse function of R1 and R2. Okay, so if R1 and R2 are large enough, the error term becomes very small. And in this case, Rout is nothing but RO2 times 1 plus GM2 R2. It's very similar to the MOSFET case. Okay, it's approximately GM2 RO2 times R2. What is VN? No, VN is nothing but you have an extra I in R1 here. Okay? And similarly Vout min now changes. It earlier used to be VC sat 2, but now you have VC sat 2 plus Iot R2. Okay? So now you have the extra headroom you need to give for the resistors. Okay? Finally, we come to the BJT cascode. Okay? This is very similar to the MOSFET cascode, right? You can show that the minimum voltage is nothing but VB3, delta VB will be almost 0 plus VC sat of 1. Okay? Now here the bipolar is actually slightly different from the MOSFET. The output impedance is just a function of the cascode transistor RO2. Okay, and you also have an extra half factor. Okay, so it's actually output impedance is B0 R0 over 2. You can try calculating it. Actually, you should take that as a homework, or we'll do it as a tutorial next week. Or I mean, we'll probably give it as an official homework. But you can try calculating and proving that this is actually B0 R0 over 2. What is this? This can be, I mean, VB is going to be somewhere around 0.7 volts, and VC sat is going to be another 0.2 volts. So this could very well be approximately 900 millivolts. So it's actually much larger than the simple current mirror. So you have a direct trade-off between output impedance and the minimum voltage. And yeah, so there are a bunch of other types of current mirrors. Okay, other bipolar current mirrors. So you have something called the Wilson current mirror. Okay, you have something called the Widlar current source. Any bipolar book you take will will have this. Should just take a look at them. They're quite interesting. It shows you the evolution of a lot of these using just 2 or 3 transistors and resistors. They figure out different ways to make current sources. Some of them have inherent DC, like the Widlar, for example, has an inherent DC imbalance. Okay, but I mean it still gives you enough output impedance and so on. Okay, so it's a little bit simpler. And so these things, I mean, they're definitely of interest to some, certain for certain applications. Okay, so we'll probably not be looking at these in any detail. Probably 1 or 2 of these might end up in your homework. I don't know, maybe just the Cascode. Okay, but since we are going to concentrate mostly on MOSFETs, we'll probably stop with bipolars here. So what we'll do is, we are pretty much done with current mirrors. Okay, so this is as far as basic biasing goes of your transistors. Starting from next class, we'll start looking at differential pairs, large signal, small. Have you studied large signal characteristics of differential pairs? No, you have studied small signal, but not large signal. We'll look at that in tomorrow's class of both bipolar and MOSFETs. Okay, and then so what I'm planning is, on Tuesday's class, there is a chance that I won't be available. So we'll have a tutorial on Tuesday's class. So what will happen is the TAs will come around. I'll also assign a homework, okay, starting from next week. So what will happen is that we'll give you a couple of problems to do in class. Okay, you try them out, ask the TAs if you have questions, if you have doubts. And maybe at the end of the class, they can also work out maybe one of the problems in class. Okay, I just want to make sure you don't have any, you're not making any, very simple mistakes. Okay, that's the reason why I want them to work out in class. And then after that, you will have several problems which to do with homework. And obviously the homeworks are meant to be done individually, not as a group effort. If we find out that there is group effort, there will be group marking also. Okay, so if we find out that people have copied from each other, we'll divide the marks accordingly as we deem fit. Okay. Okay, see you tomorrow, or see you on tomorrow afternoon.